We will now discuss about the components of a vector. Graphical method of adding vectors has few difficulties in practical usage. Adding vectors graphically using a ruler and protractor is not often sufficiently accurate. Also, it is not useful for vectors in 3 dimensions. Let us do an imaginary case study. Consider a Cartesian coordinate system consisting of x and y axis only. Let us consider that in this coordinate system, any vector should either be parallel to x axis or parallel to y axis. Let us see how to add vectors in this imaginary system. Consider a vector a bar, which has 5 units of magnitude and is directed along positive x-axis. Consider another vector b bar, which has 3 units of magnitude and is parallel to positive x-axis. Now we need to add these 2 vectors. Using tail-to-tip method, we shift the vector b bar such that its tail coincides with the tip of vector a bar. Now the resultant vector obtained by adding these 2 vectors would have a magnitude of 5 plus 3, which is equal to 8 units, and is directed along the positive x-axis itself. Extending this process to vectors directed along or parallel to y-axis, we say that adding 2 vectors d bar having 4 units of magnitude and is directed along positive y-axis and e bar having 3 units of magnitude and is parallel to positive y-axis. Now to add these 2 vectors, we need not draw the 2 vectors graphically, but can say that the resultant vector, obtained by adding the vectors d bar and e bar, would have 4 plus 3, which is equal to 7 units of magnitude, and is directed along y-axis, or parallel to y-axis. Both the representations are equivalent to each other. Note here that a negative vector would be directed along negative x or y axis. So adding any number of vectors in this imaginary system is pretty easy. Add the magnitudes of vectors, taking into account the sign, to get the magnitude and the direction, either along positive or negative axis, of the resultant vector. The most important point to note here is that we need not draw the vectors graphically each time in this scenario. We can simply add the magnitude of the vectors to get the magnitude, along with the direction, of the resultant vector. Now back to real world, wherein the vectors will not always be parallel to either axis. There would be scenarios where vectors would not be parallel to either axis, but directed along an angle. Now if we somehow represent these vectors, which are directed at an angle to the axis, in terms of vectors parallel to the x and y axis, we could use the process we have developed previously, which would simplify the process of adding vectors. Can you think of a way to represent this vector in terms of vectors parallel to coordinate axis?
Yes. We can draw 2 vectors, one parallel to x-axis, and another vector parallel to y-axis, such that adding these 2 vectors gives us back the original vector. So we represented the original vector in terms of 2 vectors, each parallel to the axis.
Very good. The process you have explained, that is, representing a vector in terms of vectors parallel to axis, is known as resolving the vector into its components. The two vectors are known as the components of the original vector. More formally, a component of a vector is the projection of the vector on an axis. We'll now discuss the process of finding the components of a vector. To find the projection of a vector along an axis, we draw perpendicular lines from the two ends of the vector to the axis. The projection of a vector on x-axis is its x component. Similarly, the projection of the vector on y-axis is its y component. A component of a vector has the same direction along an axis as the vector. In general, a vector has three components: x component, y component, and z component. Since we are dealing with vectors in two dimensions only, for now, the component of these vectors lying in x and y axis along the z-axis is 0.